Good morning, gentlemen and ladies. Eddie Wang from Houston, Texas, representing Vice Renewables Group. If you look at the brochure, we were talking about geothermal energy strategy for airport energy independence. It was a subject that was really interested introduced to the participants into this conference. We were invited really at the last minute, so we were really stretched by time to prepare such a more focused subject. Instead, discussing with Ken Wisian, which is my invited guest to this conference from Austin, Texas, we want to change the subject to the overview and the state of the HotRock research at the Bureau of Energy, Economic Geology at UT Austin. Ken has been presenting that for the conference yesterday. We want to go a little bit deeper into it, and within this research subject, we will touch base on some practical airport applications, and because we're giving a little bit more time here, I wanted to make this kind of presentation become more interactive. So during this presentation, and I want to make it more of a discussion session. During the presentation, if you have any question, please raise your hand, and we will try to entertain your question and make this more interactive. Okay, not purely just one-side talk. Yeah, please make this a more relaxed session. We have another 7 minutes to go. Thank you very much, and without having further ado, I give the talks to Dr. Ken Wisian.
Thank you, Eddie. Okay, we will connect this to one of the themes of the session, which is exploration. We talk on it. I think the audience is mostly engineers from what I've seen this morning, and I'm a geophysicist, but that hopefully will generate some questions for you. Don't be afraid to ask questions as we go along here. I'll start off with a little bit on our organization and just where we're coming from and what we're doing, and then get into some of the differences in exploration between conventional hydrothermal geothermal systems and geothermal anywhere, and then start to look at a specific case study that we've worked on making a small airfield in Houston, Texas, energy independent using geothermal energy. So with that, we'll get going. Our organization, if you weren't here yesterday, is part of the University of Texas. We're a 150 to 200 person research organization on applied geoscience, energy, and economics, where those things intersect. And we've been in geothermal. Okay, one second, complete. We've been in geothermal for quite a while, doing foundational work since the 70s and 80s. We do have a industry consortium launched now to solve problems that are common to multiple parts of industry. So if you're interested in that, get in touch with me. Our research team, another difference between us and a typical university is we are more peer professor research groups. We have a relatively small number of students and most of the professors. So our top line here is all professors with a little bit of student, graduate student, and technician support. So it's a little bit of a different structure from a typical university where you may have one professor and a half dozen or a dozen graduate students working on it. Our focus areas are broad, essentially anything from the wellbore out. So we've been doing a lot of work on resource evaluation that gets into the exploration part. Some on the subsurface engineering. We've got some work going on machine learning applications to real-time drilling data so that you can identify fractures better and counter them. Instrumentation, direct use and power generation, which I'll touch on briefly, and particularly the economics. So tying an entire potential project together and looking at the 20-year financial status of a project, depending on what engineering and resource choices you make. And then the data and machine learning ties into all of that, as every field of science and engineering now. If you're not machine learning fluent, you're a little behind the times. That's our consortium at this point. Punch through that. Okay. Besides the professors that we bring, we also have one of the largest core and well log libraries in the world. It's an immense facility. If anyone remembers the movie The Raiders of the Lost Ark, where they're wheeling the cargo in this massive warehouse, see, that's what it feels like when you walk into this warehouse. It's a couple of 100 meters back that way. We also have high temperature rock physics labs, our own ability to measure thermal conductivity at high temperatures, and so on, plus a full suite of other labs needed for anything to do with rock physics and core samples. And we do a lot of work, federal funded, military, state funding, some in-house funding for R&D. Private foundation funding is also a significant part of what we do. There are major private foundations which are supporting the research in green energy, including now particularly Interspace Foundation. If you haven't heard of that, that is now probably the largest private donor for geothermal research in the world. Jamie Beard leads that. She has a great TED Talk if you haven't seen it. But they've got a substantial war chest to disperse over the next few years for geothermal research worldwide. And their current #1 project is essentially creating a uniform worldwide database of heat flow. And that's a major multi-year project. They're working with partners all over the world. We're doing a little bit of that on ourselves in Texas. But that's going to be something that all geothermal work worldwide will be able to draw on for a standardized common reference quality of heat flow and temperature data. Okay, so let's get into a little bit of the meat of it here, hopefully generate some questions. Geothermal exploration to date is, I've got a reference there that probably most of you will not catch from early American TV, but the Jed Clampett of the Beverly Hillbillies method of exploration. Basically, almost every geothermal system that's producing today was discovered by someone walking along the ground and seeing hot water or steam or other evidence of a geothermal system. Then you call in the exploration science and try to refine your picture. But it's still largely a matter of eyeballs spotting the resource bubbling out of the ground at some level. Now, typically, you then add in various types of geophysics, magnetotellurics, gravity measurements for figuring out your structure. Space geophysics is coming in a lot more now, using Landsat, looking at vegetation or mineral contents on the surface, as well as now INSAR, so very high resolution LiDAR surveys are starting to prove useful too. The subsurface work, obviously, drilling exploratory holes, doing a temperature survey with shallow slim holes is also a common first step, which I've been a part of many of those projects. And then the water chemistry, which so far in this conference I don't think we've heard much of, but that estimation of reservoir temperatures using the water chemistry, which is a detailed specialty in itself. But you work up, starting with the lowest cost to the highest cost generally, and typically the last thing you'll do are some level of well drilling, whether it's just, again, a survey of shallow wells, starting to do a deeper exploration well, or an exploration/production well to test it out. That's relatively unique, although every hydrothermal system is its own study. But with the geothermal anywhere, you're flipping a lot of things around. So you're not looking for the water in the ground, you're looking for dry, hot rock, preferably pretty tight rock, low permeability, low porosity. So you're flipping almost everything on its head when you're looking to mine heat from the rock directly, as opposed to the fluids in the subsurface. So typically, well, you won't have a surface manifestation. You don't generally need chemistry because you're not interested in the fluids, and you're only interested in the really deep temperatures. So the shallow surveys often don't need as much, but you still need a lot of that geologic foundational work. You still have to know the rocks there, you know the structures. And I'll show you what we've done on that in just a minute. Anything to this point? Okay. Just as a sample case, here's a project we're finishing up right now, which is examining the thermal conditions for a local government. So the county of Presidio in Texas, this is far west Texas, this little pie-shaped wedge here is Presidio County. This is Mexico over here. And this is about 100 kilometers from top to bottom of the county. So the county has 10,000 square kilometers and a total population of 6,000 people. There's more sheep and cows in the county than people. So not a huge amount of electricity demand, but they're sitting on a fair amount of resource. And our main source of data is oil and gas wells, and therefore bottom hole temperatures. It'd be nice to have more detailed logs, but usually don't have that. So what we rely on are bottom hole temperatures. And you can see that the density of oil and gas wells can vary tremendously. Up here, you're getting into what's called the Permian Basin, one of the most productive basins in the world. But down here, not so much. If you get down to the southern part of the county, there's been nothing drilled. So complete absence of data there. But we get enough bottom hole temperatures to start to build up a picture. And what you see is a definite zone, of high temperature along the border here, with a sharp change into fairly average gradients, 30 degrees C or kilometer or so, back in this area. But along the border, a very high temperature zone. This is right on the edge of an extensional terrain, so a basin and range kind of system. But the section here, pretty complex. Not as complex as Taiwan, but still complex. It's a mixture of volcanics and carbonates. So, and then it hits basement at a fairly shallow depth. So there's also a distinct change in the basement elevation. Granites are higher here than over here. So you put all those bottom hole temperatures together, and you get really a very scattered picture. The data is all over the place, but if you break it geographically, those low temperatures here, the high temperatures here, and what you see is a pretty good gradient. Here you're hitting 150 C by 2.5 kilometers down. It's not bad, and you're just getting in the basement. So for the drillers here, you're drilling through a lot of alternations of hard, soft rock, and then eventually getting into the granite. But that is enough to give us a picture of, well, what's the minimum depth we're going to have to drill to get to a minimum viable temperature to do electricity production. Now, we'll apply some of that to a project we've been working on off and on now for about 2 years on the south side of Houston, Texas. And that is called Ellington Field. I'm sorry, this is a little bit small. The center of the city of Houston is about up here. The coast or Galveston of Texas would be down there. We're right on the outside of the Houston city limits, although there's more areas down here. Big NASA headquarters is down here. And the airfield outline you can see here, the runways and the buildings that support it. So this is an airport that's shared by the military, by NASA, and by the city of Houston for commercial flights. It is inside the city limits of Houston. And the Air Force actually funded us and a startup company called Sage Geosystems out of Houston to the tune of almost $1 million to do a 2-phase design or a resource assessment design project here, which completed last year. Now they're in negotiations. It's just between the Air Force and Sage. I'm not involved in it, to move this beyond the study and actually break ground, hopefully, and do the project. But the original design goal is a 3 megawatt system minimum that would essentially power the airfield. If you throw in NASA's work down here, and that would maybe boost it up a couple more megawatts, but not too bad. But the goal is to take this airfield and make it independent of the main power grid. In Texas a couple of years ago, we had a major winter storm that knocked essentially our whole grid down, in some places for days and other places for weeks. It really got people taking seriously the need to have unbreakable power in critical infrastructure. And that's where the airfields or hospitals, major transportation hubs, fuel refineries, all those kinds of things come into play as early targets for geothermal development, especially geothermal anywhere, where you can site the wells where you want the power. So in our design study on this, by the way, I don't have the temperature depth curve here, but the wells are designed to hit 175 to 200 C at about 4.5 to 5 kilometers down. In this case, entirely in a sedimentary section. So all sandstones and shales. The target depth will be a very tight shale that allows you to create a good fracture system. So let me see, I don't even talk about that. And this was also very deliberately chosen as a site by me because we could do the same project in the western US in California or Oregon and be great if it were successful. But a successful project here in the oil capital of the US, Houston, Texas, would get attention for geothermal that the same project in California would not. So it was a very conscious choice to go here. So what's the design system look like? It is single well system, 2 wells, but each well is an independent system with coaxial flow up and down inside the well. A little hard to see there. Let's see. Yeah, so you have an inner lining and an annulus, and you can flow up the outside, down the inside, or vice versa. And the heat exchange mechanism is essentially a 1 kilometer tall vertical fracture coming off the well. That's done by Sage Geosystems. Their mark is up there. And they have the IP on doing a gravity-based vertical fracture system. Now they envisioned also stepping out and doing multiples off each well, in this case 4, and then 2 total wells like this, identical, that would generate a minimum of that 3 megawatts at the end of, I don't remember if it's 20 or 30 years time, because you'll have a drawdown on the heat production. It'll start off about 4 to 6, finish up by 3 megawatts at the end of 30 years. There is also a cost estimate on here. This is a few years old, and now this system has been tested in an actual well in South Texas last year, and then 2 years ago, and then again last year. They'll be re-entering it soon. And as a great example of why you actually test this out, the concept going in was you flow water continuously, or in this case actually CO2, continuously through the fracture, in one side, out the other, and up, or you do it in the opposite direction. So they tested this out in a dry gas hole in South Texas. And on a whim, decided to also try what's called huff and puff. So just pumping the fracture up, letting it sit for a minute, then letting it close and push the fluid back out. And they actually found more efficient heat harvesting from doing a huff and puff than doing a continuous flow through the fractures. So they're adjusting their thinking now to where, for instance, if you had 4 fractures, probably more independent than strung out in a serial fashion there. But you run them like a car engine, alternating each fracture's pumping and deflation so that you get a continuous output. So, very interesting result that no one was really anticipating on how you would actually manage your system there. Oh, so I was getting back to why that's an old estimate. Now that there's some drilling experience in creating the fracture systems and testing them out, I think you can probably knock a fair amount off that top figure there. But this is an all-inclusive estimate early on of $40 million that includes the surface installation and a microgrid on the surface to make best use of the heat. For that, minimum 3 megawatts at the end of 30 years. Bearing in mind, again, this is a first of its type system, so you can expect a pretty sharp price decline as more options are tried. Any questions or comments on that? Yes?
Again, 2 questions. This hot dry rock, why would there be a decay on a drawdown?
You're still, okay, good question. So just to repeat it, if it's dry rock, why would you still have a drawdown? You're still going to be pumping heat out or drawing it out faster than that natural heat flow from the crust replenishes it. So it's exactly analogous to a drawdown cone around a water well, except it's 3-dimensional. So you will cool off the rock. You're mining the heat from a fairly set area. So tens of meters out from your fracture at most. So you've got a fairly set amount of heat. And this can be very well modeled. Numerical models of this are probably more accurate than modeling a hydrothermal system where you've still got some fairly significant unknowns. So yes, you will mine heat at a definite rate out of the area. But then that brings in, again, the possibility of maybe you stage wells over time. Kind of like letting an agricultural field lie fallow for a while and letting it recharge. You can do the same thing. And again, you'd model it, but roughly letting it lie dormant for as long as you mined it would probably be a sustainable system. Does that answer your question?
Yeah, sure, but I mean, why couldn't you just extract the heat in the correct amount to...
at a purely sustainable rate.
Yeah.
Good question. So, yes, you could take the heat out at a lower rate, but the replenishment rate for dry rock is not very high. I mean, the total heat outflow from the Earth on a continual basis is 47 terawatts. And that's a lot, but that's not nearly as much as you'd be drawing out if you got that down to milliwatts. So that's, well, that's 60 milliwatts per square meter, roughly. So you would have to have quite a large area to draw at just that replenishment rate.
Okay.
Now, you could also do other things. You could stage wells vertically, drill deeper. There's a lot of ways you can do it. And you can manage it by just leaving that one alone, letting that natural heat flow recharge it. But then you're really probably, this is outside my area, then you're probably really getting into an economic issue of how many wells would you need to generate the power you need at that low an energy withdrawal rate per well.
And then talk about using the CO2 as a working meter.
Yes, okay, good point. So yes, this system is envisioned to be a CO2 system. So that is, I mentioned yesterday, another Texas institution, Southwest Research Institute, is a leading developer of CO2-based systems and the turbine generators for them. So the idea is to do an entire CO2 system up and down. Now that will be quite an experiment because no one's doing that. There's some geochemistry that will need to be discovered as we go. But they're hoping to do a field trial on that test well of this complete system with a generator on top before the end of the year. Now, I don't know if that might be a water-only test. I don't know if that would be a CO2 system test. But that was the goal here.
radius, I think that would be quite high.
Probably so. That's definitely outside my knowledge area. I'm a rock guy.
So, excuse me, is that the similar type of technology that the Sage announced the other day about the earthen battery?
It is similar. So I have not been a direct part of their research, but we do seismically monitor their tests. So in their test well, where they did create that fracture, and by the way, in creating that fracture, we saw no observed seismicity. But again, that ability to just pressurize a large fracture and then withdraw it when you want. So far, the experiments showed a better than 80% return of energy out versus energy in. So I think there's a lot of potential. And what we're seeing, Texas, by the way, has a very large wind installed capacity. But there's intense interest on what can we do to level out our wind and solar so it's more of a base load. And the ability to scale up a battery that works on this type of principle is huge. You can drill a well next to every wind generator if you wanted to, and do that faster and more environmentally friendly than building a massive lithium battery bank. So I hope there will be a field trial. I know there's a power company in Texas that's very interested in trying this kind of system out adjacent to a solar farm. But the bottom line is, you can pressurize a fracture and cycle it almost indefinitely between fracture propagation pressure and closing pressure. As long as you can manipulate your pressure really well, and that gets into many of y'all's subject areas, but as long as you control that pressure well, then you can cycle that rock indefinitely. And that's what they're going after. And it was a serendipitous discovery of the fact that the huff and puff was such a promising method of working a fraction. Good question. I think I saw another one. Yes?
Well, if you would realize temperature drop over time, do you see any chance if you withdraw less energy from the well that the well can recover over time, or once it's cooled down, that's gone forever?
No, fair question. So yes, you can adjust and manipulate how much energy you're drawing out. So you're going to have a decline curve. There's no way around that. But you can adjust how much it is, how fast, where that eventual level off point is. And for this system, it would pretty much level off about 3 megawatts. So you can adjust it. But as mentioned earlier, to get it to actually recharge, you'd have to drop to a very low level. So you might as well just turn it off for a while and let it recharge that way. There needs to be more modeling on that. I know Sage has modeled it, but that data hasn't been released. I'd like to do that myself and look at it, in a scientifically publishable way. But the fact that you're not dealing with a fluid, you're only dealing with the solids and the heat conduction equation makes it very susceptible to good modeling and very accurate modeling. Was there another one? Yes.
I want to give Dr. Lee some input about the CO2 turbine. Ready that? The CO2 turbine has a very wide range of applications in the industry, and I personally witnessed the design, construction, and the testing of the 3 types of turbine in Southwest Research Institute in San Antonio, which has been successfully tested and going into pre-commercial installation and hopefully commercialized in the next couple of years. The high pressure, what I see in the mid-entropy application in geothermal energy fields, if you look at the pressure and a temperature curve, it's like really like a hump, okay? And the highest temperature, pressure I've seen there is around 23 megapascal. And the turbine, the 3 megawatt turbine tested by Sage, and which has the proprietary ownership, has a spin speed of like 14,000 RPM, very high speed. Yeah, it's about half the size of my body, so it's very compact. And SCO2 application down the road will have a very small footprint. So if we are talking about commercial scale geothermal power plant, 300 megawatt, I think the size of the fuel required for a like coal-fired 协和电厂 is only a quarter of that. 1/4的这个场地 will be sufficient for such an installation. I can give you more information about the development of the SCO2 turbine. We can discuss that separately. But I think you have a very interesting question, and I think the industrial is make sure that it's safe and operable at this stage of the game. Yeah, like we mentioned, there are so many regulatory issues surrounding the new technology in geothermal applications, and this is probably one of the areas that we need to address.
More? Yes.
One more question. Yes. Speaking of the carbon dioxide capture, the discussion is related to UT has any partner work that study on this carbon dioxide capture, like for example pressurized down there in the wells and carbonated solutions that we can work in the future together?
Yes, definitely. So I actually run 6 different research groups at the university, and one of them is a world leader in carbon sequestration. And they are actively studying exactly what you're talking about. Happy to make the connections there. Other parts in the engineering school are studying the capture aspects. And now we're starting to look at, as you know, if you're doing a carbon capture and sequestration project, you don't want to use dirty energy to do it. So now we're starting to look at, well, what would be the economics of coupling a geothermal system to power the direct air capture and sequestration? So now there are current capture and storage projects launching all over the south central United States, but they're all using pretty conventional energy sources right now, but they're going to be getting up into the megatons per year pretty quickly on sequestration. But happy to make further connections on that.
Sure.
Let me back up for 1 second. Maybe we'll get to some more here. But one thing I wanted to point out that I didn't mention earlier. Yeah, no, it's better on this. Okay. So, a nice thing about geothermal anywhere is the temperature in dry rock doesn't vary that much from kilometer to kilometer. It's a fairly slow change. So that gives us also great flexibility on where to site wells within a facility. Again, you want to site them on your facility. That way you're minimizing transmission, you're making them more secure. And in this case, the main limit was where can we find enough open space within the military side of the airport to set up a full-size drilling rig. And so what we settled on was just an open spot, about 2 acres worth, right in the middle of the base, right here, that wasn't committed to anything else, that we would do the drilling, install the surface generation right next to the wellhead, and move on from there. Now, if you're doing the whole airport, of course, obviously you've got a large amount of area that you can work with, but you also don't want to interfere with aircraft operations, so that's why we went off over here. But anywhere where you have a little bit of open space in a facility that needs unbreakable power, and you've got reasonably warm ground, this becomes really viable. I think that we all are aware of this. Most of these are common to all geothermal, but in particular for the geothermal anywhere, that ability to site things right where you need the power really eliminates some logistics issues. And it's also, again, here, and really good or any place that has to pay a lot to import fossil fuel? Okay. I think, yep. That's all prepared stuff. We do have some time, or get time back, but are there any last questions on any of this, or do you want to dive deeper on any of the topics? All right. Well, thank you very much. Thanks, Eddie, also.